All right, guys, I think I'll go ahead and get started. Thanks for coming. It's good to see all of you here for our second and final review session for Math 350. This is the last time I'm going to talk about this stuff for a while. Oh my gosh. Um, anyway, for those of you who are still working on your proofs, again, anytime I'm around, you're welcome to come on in and get those written up. I think several of you already have, so that's great. But I will continue to do that. And I took another look last night at the sample final that I put in Canvas. I really liked those questions. This is a pretty good thing to look at, I'd say. Practice some of those problems. So if you haven't done that yet, I'd recommend, well, we got about 24 hours roughly until it's go time. So I would recommend getting on that maybe later today or something. If you haven't looked at it. If you have, that's great. Certainly good. And I'm just going to kind of pick up where I left off. I really felt good about the review on Saturday in terms of the coverage that we had. We got a lot of things done. And if you missed any of that, I did send out a YouTube for you, and you are certainly able to watch that whenever you'd like. And my goal for this session is really to just kind of do more of the same, but maybe try to hit some specific topics that maybe I missed a little bit or that we didn't do quite as much with on the last review. At some point, I'm going to actually probably end up doing some of the problems that are in the resources folder. And there's a set of review problems in that folder. It's pretty long, actually. So instead of just leaving you to your resources to do all of those, I might do a few of them here as well. So I figure that's fine. It doesn't really matter. And as always, if you've got questions as we're going along, just jump in. There's no schedule for this. There's no rush. I don't really have an agenda. We'll get through as much as we get through. We could obviously sit here and do problems for, from now until tomorrow. At some point, we have to kind of just call it good. So I'm not really in any particular agenda as far as this goes. But so I'm going to start off with a question, and I'm going to pick up my numbering with where I left off on Saturday's review. So numbers 1 through 8 we already did over the weekend. So we're going to start with number 9 here. And by the way, if you've looked at those problems that we did on the weekend, in a lot of cases there was some basic definition that you needed first, and then you use that definition to do something, or it might have been a theorem. So maybe, and you've even seen this on my midterms, right? That I like to sort of do these 2-part questions. Part 1, tell me what the mean value theorem for integrals says. Or just give me a definition or a theorem. And then the part B is that, okay, now let's use that to, do some problems. So that's a good way to think about how I haven't written the test yet, but that's what I'm kind of thinking about. I'll probably do something very similar. There'll be some definitions and theorems with a question related to it below. And then another definition or theorem with a question related to that below, that kind of thing. So anyway, so in this case, number 9, I'm going to suppose that F is going from a closed interval a, b to R. Danny, are you able to see and hear this okay out there? So let's suppose that that's continuous. Danny, can you see this and hear this okay out there in Zoom land? I just want to make sure before I go too far that I'm not. Actually, there's a bunch of people in here now. Louise, Nazgul. Can anybody hear me out there?
Yes.
In Zoom? Yes?
I can see it.
Can you see it?
Yes.
Okay, and you can hear me?
Yes.
Okay, just making sure. All right, so suppose we have a continuous function. Boy, right, we could stop right here and say, well, how many things do we know based on this, right? If we have a continuous function on a closed interval, tell me some things that you know. It's uniformly continuous. What else? It's bounded.
Riemann integrable.
It's Riemann integrable, right? So it's Riemann integrable. It's bounded. It's uniformly continuous. We have a intermediate value theorem. We can do location of roots, all those big consequences of continuity. We do have to be careful that if we say the function is continuous, that does not mean that we have a derivative that we can work with. So don't start applying anything about a derivative unless you see the word differentiable there, right? So far we just have this, and is continuous, and I'm gonna throw another word in here now that we didn't really talk much about last time, and it's been a while, but I'm gonna assume that my function is 1-to-1. Then if f of A is less than f of B, prove that f is strictly increasing. Okay, so if f of A is less than f of B, it is strictly increasing. Now, guys, one of the ways to characterize strictly increasing is that the derivative is positive. But see, we don't know that we have a derivative here, so that particular route for a solution isn't going to work here. But if we don't know that we have a derivative, we shouldn't be thinking about f prime of x. Okay, so we don't have that. So we have to think about this in sort of more fundamental terms. I would recommend that it's not a bad idea to just kind of sketch something here for yourself. Let's make a closed interval at A to B like that, and f of A is maybe right here, and f of B is right here. And we've set this up so that f of A is less than f of B. So the first thing is to just even convince ourselves, do we believe this statement, right? Do we believe that our function has to be strictly increasing? If it wasn't strictly increasing, and remember, I have to be able to draw it from here to here without picking up my pencil. It's continuous, right? So if it wasn't strictly increasing, what would happen? Well, we'd have to come back down a little bit, something like that maybe. But now, if this happened, we would have, say a C1 and a C2 not equal to each other, but f of C1 equal to f of C2. And that would violate the 1-to-1 condition, exactly. So in fact, intuitively, this picture kind of tells the story. Does it seem reasonable? A 1-to-1 function has to pass the so-called horizontal line test. You should not be able to draw a horizontal line that passes through your graph more than one point, right? So this would not work. So what might be a strategy here would be by way of contradiction. Yeah, because we've already got the contradiction picture on the board here in front of us. So why don't we try and see if we can prove this by way of contradiction? So solution. This is going to be by way of contradiction. So let's assume that f is not strictly increasing. Now, by the way, strictly increasing, just to remind you again, strictly increasing just meant, we wrote this down as a definition at some point, that if x is less than y, then f of x is less than f of y. That's the definition of strictly increasing. And of course, there's usually an interval involved, but in this case, it's the entire interval from A to B. Okay, so if f is not strictly increasing, then by way of contradiction, that would mean that there exists an x less than y in the closed interval from A to B with, what would it be?
F of A greater than F of B.
F of x.
Oh, yeah.
Greater than or equal to f of y. Exactly. So that would be the assumption by way of contradiction. Okay. So let me kind of go back to my picture and label those points now. So we might have, x is here. There's f of x, and then maybe y is here. And there's f of y. So I've set up a picture that kind of reflects this. Here's f of x, which is now greater than or equal to f of y, as you can see visually from the picture. So doesn't hurt to have the picture there. It's not going to get you a huge amount of points in terms of the solution, just because it's more or less intuition based. It's not very rigorous, But it will hopefully help guide you a little bit on how to think about this. Okay, so I'm wondering, does anybody see a way to get a contradiction?
I was gonna say we could use off the bat, we could probably use the fact that it's 1 by 1, 1 to 1 to prove that it can't be monotone.
So I actually think that the way we're going to logically get to our contradiction here is we're gonna end up proving that F is not 1 to 1. Okay, so we've
Oh.
already got our contradiction approach going at this point. We're assuming F is not strictly increasing. I don't know whether this is, if I say it's not strictly increasing, that doesn't tell me whether it's monotone or not. It could wiggle up and down a lot, right? It might not be monotone at all. But I'm gonna try to convince you now, guys, that this function is not 1 to 1. If we have this situation, if you see this, you can see that it's not 1 to 1 from this picture. So I'm wondering if anybody has a thought about how to. So what I need is I need 2 different inputs that will have the same output. Right? Now, I don't know that I'm gonna have a different input that has the same output as the f of x. The way I drew the picture,
Mhm.
the f of x
But the
looks
f
like
of
it's the
y
highest
might.
point. There may not be anything, I
But
mean,
the f of y, we probably might.
yeah, the f of y, isn't there gonna be a point over here? One more time.
Intermediate value here?
The intermediate value theorem. Guys, take a look. We have f of a way down here, and we have f of x way up here, right?
Mhm.
Those 2 values are like this. And f of y is like a k value in between those 2 values. So what we're gonna wanna try to do here, guys, is let's apply the intermediate value theorem. Remember that came before we talked about differentiability, so we don't need a differentiable function for that. But we're going to apply it on what interval?
A to x.
From A to X. Yeah, X is right.
Yeah,
So
A to
from
X.
A to X, from here to here, so on A to X. So what does that tell me? It basically tells me that since F is, so I'll put a colon here, since F is continuous, there exists a C in this interval from A to X such that F of C is equal to, so now I'm looking at, I could take any value that is between F of A and F of X. Right? Remember how the intermediate value theorem works? You have F of A, you have F of B, right? And so if you evaluate those 2 points, then any point between those 2 points, which we call K, there has to exist a C such that F of C is equal to K. Well, guys, F of Y looks like it's between F of A and F of X, so we can apply it as such. Okay, and this is since A is less than X is less than Y. And that's actually fine. Pardon?
Oh,
By the way, I
because we
should,
know that f of y is less than x.
so I wrote.
Because f of y is between f of x and f of a.
Right,
Okay.
right, so let me just say it that way, sorry, let me just change this. So since F of A is less than or equal to F of Y is less than or equal to F of X. Right. Okay, does that make some sense? So this is a value that's between F of A and F of X. And if either one of these was actually an equality, you would already have contradicted 1 to 1. And so here X is less than Y, so if F of X was equal to F of Y, we're already done. So you could actually, if you wanted to, you could have made that point up here. You could have said, look, guys, if F of X equals F of Y, then your function already fails to be 1 to 1. So you might as well assume that this is strict. So now you've got f of y strictly between f of x on this side and f of a on this side. But now this, in this case, since c is less than or equal to x, which is less than y, c is obviously not equal to y, and so that means that f is not 1-to-1. So in that case, the function would not be 1-to-1. So we proceed by way of contradiction to prove that a 1-to-1 continuous function must be strictly increasing, assuming that the f of a is less than f of b. Of course, if f of a was greater than f of b, it would be the other way around. Okay, does that make a little bit of sense? All right, so I kind of like that one. A few others that we didn't quite get to last time. I did that one, I did that one, I did that one. Did that one, that one, that one. Oh, yeah, let's try another one here. Questions? Everybody okay with this? All right, I'm gonna erase this side here. And let's go on to number 10. If x is greater than 8, prove that the square root of x, the square root of 1 plus x is less than or equal to 8, x minus 8 all over 6 plus 3. Okay. Any thoughts about what this topic would be? Like, where is this coming from?
Taylor's theorem?
It's kind of like Taylor's theorem, isn't it? Yeah. I would argue that because we don't have higher powers of x here, it might just be the special case of the regular mean value theorem. The mean value theorem really is Taylor's theorem in the case of n equals 1 or whatever. But yeah, exactly right. So if we're going to use that, we would have to have a function identified. We would have to have an interval identified. So what function do you want me to consider here? How about the square root of 1 plus x? Okay, so let's do that. Let's let f of x equal the square root of 1 plus x. And does anybody have an interval in mind that I'm going to try to work with for this application? This right here? That actually creates the interval for you. We've seen this so many times, right? If you just have this little assumption, you can make an interval out of those two values. So I'm going to consider the interval from 8 to x. Okay. And so what I can do is just apply Taylor's theorem, or more specifically here, we can apply the mean value theorem to find a c in this interval from 8 to x such that f prime of c is equal to, it'll be f of x minus f of 8 all over x minus 8. The real big thing you want to do is you want to be looking at a question like this and recognize that it is a good problem to use the mean value theorem on. Right? That's, you really want to kind of jump all over that. If you do see that, then the rest of this is just kind of, I'm just going on autopilot right now. I know I can take this derivative, I know I can evaluate all this stuff. I'm just going to do all that, right? That part's easy. It's just getting the right approach first. Hey, Daniel, there's maybe, oh, Amber's sitting there. We can put another chair over here on this side. How about that? This is as popular as I've been in a while. Must be an exam community. Okay. Yeah, so let's do this. We can take the derivative of this function. Unless I say otherwise, you would be able to just use your basic calculus rules. If I really wanted to see you justify the derivative of this, I would probably ask it as part A. I said, oh, let's calculate, use the definition of the derivative to find f prime of x for this function, and then I would then go to part B. We'll just go ahead here and use it. So using the chain rule, we're going to get 1/2 times the square root of 1 plus c. And on the other side of the equation, we have f of x, which is the square root of 1 plus x, and we have to subtract f of 8. Obviously, f of 8 is equal to 3, square root of 9 is 3, and then on the bottom, we are dividing by x minus 8. So this is the equation that we have, and we know that c is between 8 and x. Right. Okay. And we want to get the square root of 1 plus x kind of isolated by itself. So what we could do is move some things around here. Let's just do a little algebra with this equality. Or the other thing we could do is we could say, all right, we don't know exactly what c is, but we know that it's between 8 and x. So the smaller c is, right, the bigger this fraction on the left side would be, right? So the biggest that this can be is gonna occur when c is actually equal to 8. That'll make this as large as possible, right? So the actual value of it would be, so let's do an inequality here. This would be, the actual value would be less than or equal to what I get when I plug in 8 for c, which would be 1/6. So I can just tack that on the left. So here I'm doing an estimate. Given that c lives between 8 and x, with 8 being the smallest number I can put in for c, then the biggest that this fraction could be is 1/6. Okay, now let's oh well, we're basically done. Solve this for the square root of 1 plus x. So I'm gonna multiply the x minus 8 over to the other side. X minus 8/6 is greater than or equal to the square root of 1 plus x minus 3. And now I just have to add 3 to both sides. And we end up with that. So, make sense? Yeah, so remember, you don't usually, you're not gonna know what the c is, but usually you're working with a function that can be either maximized or minimized at the endpoints of whatever the interval is. So that's what you wanna be paying attention to here, guys. That this 8 is a number you can actually plug in for c, and actually when you do it, you see the 1/6 come out. And you're looking at your problem saying, oh, that looks like what I need. So it's actually not so hard to make that work. Does it seem okay? Yeah, so that's just a little application of the mean value theorem. Okay, let's keep going. So I can come over here now. Just a little bit of this space. Guys, if you are out there in Zoom and you have any questions, just holler. I can't really see much on this little phone screen, so if you have questions, don't hesitate to ask me. Jump in and let me know if there's anything here that's not real clear. Okay, let's do number 11. And here is what I'm going to do, guys. I'm going to let A sub k consist of the set of the multiples of k. This is going to be where k is at least 2. So a sub 2 is the multiples of 2, a sub 3 is the multiples of 3, a sub 4 is the multiples of 4, and so on. And what I would like to do in part A of this question is I would like to compute Z minus the union I runs through the natural numbers of A sub 2I. This is all about set theory. So this goes way back to the first month of the semester. And here we're using the sort of the indexing of an arbitrary union of sets. And in fact, it's an infinite union here that we're working with. So this is technically, sometimes when I have these kind of problems, I like to just write it out explicitly a little bit. The notation can kind of confuse me easier than anything. So I might actually just go ahead and write out like the first few terms here. So like when I equals 1, we would have A2. And then union, when I equals 2, we would have A4. And then A6 and so on. And this is a dot here. Just to kind of get a feeling for what this set actually is. So this is a subtraction, which as we know is really referring to set difference. So I'm taking all of the integers and then I'm removing anything that's in this union. So need to take a minute and think about what that union actually would be. So the union, what lives in here? Well, it has to live here or here or here or here. The union is referred to as or, right? It really reflects an or property. So multiple, I have to be a multiple of 2, or I have to be a multiple of 4, or I have to be a multiple of 6.
So it's just even numbers.
Yeah.
It's just the even numbers, right? Anything that's a multiple of 4 is already a multiple of 2. Anything that's a multiple of 6 is already a multiple of 2. So in fact, all of these later sets are actually inside of this one.
Yeah.
So you can, very good, so you can just think of this as Z minus A2. So the union of all of them is just A2. And what do I get when I take the integers and I remove the even integers?
The union
The
of the
odd
odds.
integers, okay, great, so this is the set of odd integers. Okay, so maybe that was too easy.
Oh, I like this one.
You like that one? Okay. But let me give you another question.
Do you want us to write that as just odd integers, or do you want us
You
to
can
write
do
it as
that.
the union of the odd integers?
No, I would, if anything, you could just say it's a set of X such that X is an odd integer. If you wanna make it look a little bit nicer, but I would probably be just fine with set of odd integers in this class. If it was Math 302 or something, probably not, but for this purposes of this, that's totally okay. Okay, so now I have another question, part B, circle the words, if any, that apply to, and I'm gonna give you the set here, I'm going to take Z minus the intersection, where I is an element of the natural numbers of A sub 2I. And the words that we are going to think about circling are the words finite, countable, uncountable. Those 3 words are what we're going to consider, and we're going to figure out, is this thing. So now we have an extra step. We not only have to figure out what the set is, we then have to decide what properties it maybe has. And it could, oh, and by the way, I said word or words, so it could be several things apply or maybe nothing. Right, so anything is possible. We do know that a set cannot be both countable and uncountable. An uncountable set by definition is a set that's not countable. Countable, on the other hand, let's just remember, a countable set is one that is either finite or has a bijection with the natural numbers. Okay. So that is what we have to figure out. So knowing those relationships is helpful. But ultimately, to answer the question, we still have to figure out what is this set. Like we have to get a handle on it. So we're starting with the integers and we're gonna take away the intersection. So we're gonna, let's just again, that strategy worked nicely last time. Let's just do this again. Let's just imagine taking this intersection. So what am I looking at? I'm looking at the integers that are multiples of 2 and multiples of 4 and multiples of 6 and 8 and 10 and 12. So what integers are those? If I'm a multiple of 2 and I'm a multiple of 4 and I'm a multiple of 6 and I'm a multiple of 8, and of course this goes on forever, what am I?
Can I take a guess?
Please.
I'm thinking 1.
Well, 1 is not a multiple of 2 or 4 or 6 or 8 or any of those.
Oh, what? Oh, shoot.
So we're
2?
talking about multiples. So A2,
Oh,
those are
multiples.
even integers.
Mhm.
And then A4 would be the multiples of 4.
Mhm.
A6 would be the multiples of 6. So what integers are those that are multiples of all of those? But 2 is not a multiple of 4.
Oh,
It doesn't work that way.
The max would be the max.
The max of. It's like, what is that?
Yeah, empty set, I don't know.
Say it again.
The empty set?
Yes, it's an empty set. There is no integer in the world that is a multiple of 2 and 4 and 6 and 8. And so, because this is dot forever. If it was a finite list, then the answer would be the least common multiple. Anything that was a multiple of the least common multiple, but that gets a little too number theory-ish for me. Did I just say that?
Yeah, you did.
I did. Don't quote me on that. I
You
love
said you
number
wanted
theory.
to teach it next
I
semester.
do. But anyway, that's not really so good for Math 350. Anyway, for our purposes, guys, this is basically just, I guess I could make one exception. Would you agree that the number 0
Mhm.
is a multiple of 2? Because you can take 2 times something
Kind
and get 0.
of trivial, would you
Right.
say?
And 0 is also a multiple of 4
Yeah.
and a multiple of 6 and a multiple of 8. So technically, I'm going to say that this thing that we're subtracting here is actually 0. 0 is the intersection of all of those A sub 2, 4, 6, 8, 10, and so on. Okay, so we know what the set is, and now my question for you is, which of these words, if any, should be circled in association with that answer? Countable, all right, I'll circle countable. So are we gonna circle anything else?
I wanna say finite.
How many integers are there?
And
If I take one integer away from an infinite set,
so,
it's still gonna be infinite, right? So I don't think it's finite. And if you're
Can't be.
circling countable, then you can't
Can't be
circle uncountable, because those are mutually exclusive concepts. So it would have to be countable. Now, I would want a justification for this. Z minus 0 is countable since. What'd you
it
just
forms
say?
a bijection with the naturals.
Okay, you could say there's a bijection with the natural numbers and you wouldn't be wrong, but that's not providing me with the insight here. Then I would be asking you, give me the bijection, which is gonna be,
And
sorry?
Z positive is like, it's just like,
Yes.
Z negative would just be negative.
Z positive is just n, Z negative is just, I don't have a notation for it. Yeah.
Could you do like negative n? Is that like a?
We could make up that notation, but I'm still trying to get, what's the justification here? So Lizzie, you already said it, Z is countable, right? Guys, you're allowed to use facts that we know. We certainly talked about this, the integers are countable. But why does the integers being countable mean that this will still be countable? This is not the same as the integers.
It's removing.
Because removing is.
We're making it smaller, right? A subset of a countable set is countable. So, and a subset of a countable set is countable. If you need a reference on that, we can go all the way back to early in the semester, that'd be proposition 2.11. So you can use that if you need to. Okay, so we know that this is countable, but it's clearly not finite. And if it's countable, then it's not uncountable either. So anytime you're circling or not circling something, I'll probably ask for a justification. Okay, so you've kind of seen that before. All right, let's do a part C. Let's take this one. Let's do Z minus, so same question as part B. Z minus the union over P, which is gonna be a prime, so I am getting into number theory now. So 2 or 3 or 5 or 7 or so on, any of those, of A sub P. Okay, so this would be, this would be the integers minus, we take out A2. We also take out A3, we take out A5, and we go dot 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 forever. And we try to figure out, well, what exactly have we taken out? Taken out a countable set? I would agree with that. So if we've subtracted by the way, if we have a countable set and we remove a countable set, do we know what we're left with?
Accountable sets.
Has to be a countable set, so for sure, again, this is a subset of Z, right? Because it's just Z with some things removed, and this guy is already countable. So I know that this thing is countable, the only question is whether I should be also circling finite. Because remember, a countable set is one that is either finite or in bijection with the natural numbers. So, this set is countable. Gonna agree with that. And so it's not uncountable. And the follow-up question though is that finite or not as well? So far, that's not been excluded.
Is it just one?
Yeah, so you talk about what we're removing or
Like what's
the actual, what's left,
Yeah.
okay. Good point, so guys, we're removing all of the multiples of 2. So that gets rid of all the even numbers. Now we're also going to get rid of all the multiples of 3. And we're gonna get rid of all the multiples of 5. Okay, try to think about a number that you're not any number that you wouldn't be removing. So you've removed anything that's got a factor of 2 in it, you removed anything that's got a factor of 3 in it, you've removed anything that has a factor of
Which is
5 or
0.
7 or 11. Isn't every number basically made up of a prime factorization, except for
0 and 1.
0 or 1, right? Although 0, technically 0 is, I know that it's a multiple of any non-zero number, so 0 has been removed as well. So I would argue that this set is actually equal to 1 is not the right answer. But it's close.
Is it also -1?
Is it also -1? All right, I'm glad we got some, but I have to keep these Zoom people engaged. Yeah, it's actually plus or minus 1. And that is definitely a finite set. This is in bijection with, you remember those J sets we made way back in the beginning? So J sub K was just the list of the first K positive integers. So you can just do that. Okay, anyway, so yes, this one is also finite. This one is finite and countable for sure.
Is
Okay.
showing that it's the set of positive and -1 clear enough that it's then finite?
Mhm.
Okay.
Yeah, you wouldn't need to do all this. I was just trying to remind you about that. Yeah, plus or minus 1 is a finite set. Okay, we're gonna assume we know that by the end of 350.
I don't know if it's finite.
Okay,
Baker's.
let's see, let's do, well, I'm gonna go to a new problem. I'm not gonna use these sets anymore. But I am gonna continue to talk about countable and uncountable a little bit more. I think that would be good. So here's number 12. And what I wanna just ask here is to give an example of something. So give an example of a countably infinite subset of the closed interval from 0 to 1. Start off with something like that. You guys are all aware, right, that any interval any interval whatsoever is always uncountable. Right? We actually proved that. We actually technically we proved that the interval 0 to 1 was uncountable, and then we made bijections from that to any other interval from A to B, right? And remember that a superset of anything that's uncountable is still uncountable. So that's how we prove that R is uncountable, right? Because it is a superset of any specific interval. So there's lots of uncountable sets in real analysis, but within a uncountable set, we can make sets that are, again, countable. Any thoughts on how to do this? And there might be more than one idea here.
You can start with 0.4, then 0.44, and 0.44, like you just added the same number over a number.
0.4 and then 0.44 and then 0.444 and just so on?
Yeah.
Okay, yeah, I would totally agree that that would be an infinite countable subset. Obviously, the values are all between 0 and 1. That looks good. Anybody want to give me something different?
Use the ratio.
I could use the rational, so this is one example. Another example would be to use the rational numbers. I would have to intersect that with my set so that it was clearly within the set, but that would also work. Anything else? Basically, anytime you're making a sequence, it's just any kind of a sequence that's within this interval, it will be indexed by the natural numbers, which means there is a correspondence with the natural numbers that you can take advantage of. So you could do something like, 1 over n, where n is in the natural numbers. That would also work. There'd be lots of examples. So this is not anything all that difficult. But what if I wanted it to be an uncountable subset of that same interval? So let's ask it this way, I'll call this a follow-up. Let's give an example. Let's give an example of a proper. So remember, proper just means it's not equal to the whole set. A proper uncountable subset of the closed interval from 0 to 1.
Can I give out an answer?
Oh, you're so excited out there today. Yes, of course, you can jump in here, Danny.
All real numbers intersect with the interval 0, 1.
What do I get if I take all real numbers and I intersect them with the closed interval 0, 1?
A prop. It's uncountable, right?
It is, but what is it?
Isn't it just 0?
What if I take the whole real numbers and I intersect it with the interval from 0 to 1, what's that gonna be?
Just 0.
0 to 1. And that doesn't satisfy my requirement that this be a proper uncountable subset. So I want a subset that's not the whole 0 to 1. Set of 1 over n plus 1. If this one was countable, I'm pretty sure this one was countable too. Yeah.
Yeah.
Yeah, so we could use the irrational numbers somehow. Guys, actually, what you could take any of these countable examples and subtract them from the closed interval 0, 1, because if you take the closed interval 0, 1, which is uncountable, and if you subtract, so let's make sure we can explain this. If I start with an uncountable set and I remove a countable subset, if I subtract a countable subset, then I will be left still with an uncountable set. Do we know why? So if A is uncountable and we subtract B, which is a subset of it, and B is countable, then this whole thing is still uncountable. How would you prove that? Is anybody learning any theorems? Studying any theorems for this exam?
We don't like theorems, Dr. Hannon.
What was the theorem what's the biggest theorem about countable sets that we studied?
Well, that's his-
A countable union of countable sets is countable. Can I use that to help justify this? I'm bringing it up, probably. Right, guys, by way of contradiction, if A minus B was countable, then I could take that and perform a union with B, and that would be a countable union of two countable sets. Which would have to still be countable, but that would be A, right? So in other words, A is equal to A minus B union B. This one's already countable. If this one were also countable, then A would have been countable, because it's a countable union of countable sets. So, but A is assumed to be uncountable. Following me? Okay, so you can actually argue that from theorem 2.4. Countable union of countable sets is countable. So that going back to the suggestion here, if we subtract a countable subset from something uncountable, we're going to be left with something uncountable. So I could take 0, 1, and I could subtract the set of 0.4, 0.44, 0.444, and so on, right? I could do that. Or I could subtract the rationals from 0, 1. So I could take 0, 1, and I could subtract the intersection of Q with 0, 1. And what that would give me, actually, that would give me the rational numbers, sorry, that would give me the irrational numbers that are between 0 and 1. So that would give me R minus Q intersected with 0 to 1. So that would be another example of an uncountable subset. Or we could subtract the 1 over n set. But you know what? All of these examples are harder than they need to be. Well, can anybody think of a way to give me an example without sort of subtracting something that we've already looked at? Just kind of going from scratch?
Just use complex.
Oh, no, we're not doing that. Take math 412, we wanna do
No,
that.
I don't want.
I have a guess, but I'm not 100% sure about this.
Alright, go for it.
I was thinking kind of like a piecewise where like x is either a rational or irrational number.
Well, if something's rational or irrational, that would be everything. Everything is either rational or irrational.
Yeah, that's true. I was like thinking of piecewise where it's like 0 to 0 or 1.
When I use the word piecewise, I'm usually using it in the context of functions, not just for sets. So I'd be a little careful with that. Jungwoo, what did you say a minute ago? How's the open interval 0 to 1? That's proper, because it's not the whole thing. Guys, any interval. You could have said 1/4 to 1/3, or I don't know, 0.1 to 0.8. Then you could make it open or closed, wouldn't matter. Anything like this is proper and still uncountable. Yeah, so it's actually pretty easy. It's a pretty easy question to do. Okay, let's do something else. So I would actually recommend, guys, based on kind of doing these examples and getting it back in our minds, it might be worth reviewing the propositions 2.8, 2.9, 2.11, and 2.12. So I'm sure you would have learned these on your flashcards for our first midterm. These are the ones that say things like subsets of countable sets are still countable, or a superset of an uncountable set is still uncountable. Or another one was if I have a 1-to-1 function and the domain is uncountable, then the codomain is uncountable, right? Or if I have an onto function where the domain is countable, then the codomain has to be countable. So if you have functions from A to B and you know that they are either one-to-one or onto. I hate to write, I mean, I could write them all down if you want me to again, but. The spirit of the idea, I mean, they're all captured in these propositions, it's just the idea is. If your function is onto, then it's going from a bigger set. For an onto function, your input space is bigger than your output space. So that means that if this guy is countable. Then B is even smaller than that, so B is also going to have to be countable. Or conversely, if B is uncountable, then A is uncountable. There's always a contrapositive rephrasing of all of these statements. So, and then for a one-to-one situation, the picture is reversed. The input space is small compared with the output space. So if you have a function from A to B that is one-to-one, now the A is smaller than the B. So if A is uncountable, B will be uncountable. Or conversely, if B is countable, then A must be countable. Okay, so anyway, that's been a while since we probably looked at those propositions and. In fact, I think I proved these even before I was back in person.
Yeah.
It was like way back at the very beginning of the semester, so. Okay, anyway, let's move on to another topic here. I'm gonna go on to number 13. Well, I haven't done one of these for a while. Let's just do this. Let's just try to prove from definition. Prove from the definition that the limit as x approaches 3 of 1 over the quantity 4 minus x squared is equal to -1/5. Okay, so there's nothing, terribly creative about it, but these do have to be practiced or you get rusty on kind of how you have to work on these. So we would have to have the definition. This would be another case where probably part A of my question will ask you to give me the definition of what a limit of a function is. And then in part B, we would do an example that uses that definition. So just let's just recall here that the limit as x approaches c of f of x would be equal to L if and only if. So I'll go ahead and write the definition here essentially. For all epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than absolute x minus c is less than delta, then absolute, and by the way, you have to have that 0 there, right? Because x does not equal c when we're calculating these limits. It's already open for you. F of x minus L is less than epsilon. That look okay?
Which one do we not need the zeros?
When we're proving that f is continuous at c, and instead of an L, you just put f of c here, and you don't need to take out the 0. So it's a similar definition, but it is a little bit different. Okay. So this is the proof by mumbo jumbo from the sheet here, basically what we have. Yeah. Okay. So we got our proposed value for L sort of given to us. Actually, I wouldn't have needed to give this to you. I could have said calculate the limit and then prove it, because in this case, everything on the left side is continuous. I agree that when we were first learning these limits, we did it before. If you remember, I kind of jumped out of order with the book. We learned how to do these limits before we even talked about continuity. But once you know that a rational function is continuous everywhere that it's defined, the only places this is not defined is 2 and -2. So if I'm looking at the limit of this function as x approaches 3, we can literally just plug in 3 and get the answer, because that's what f of c is. Right, so anyway, I didn't have to give you the -1/5, we all could have figured that out on our own. But now that we have it, let's try and go through the definition here. So I'm gonna start my solution. What's the first line of the solution?
Let epsilon greater than 0 be given.
Yay, okay, got that part down. Let epsilon greater than 0 be given. That's our rubber stamp that we don't even really want to think too much about. We're just gonna do that right away. And then we have to figure out the delta. So I'm gonna save the rest of this space to do the rest of this proof, but I need to come over here and give myself some scratch work room. And the scratch work is really where the meat of the calculation comes into, right? So let's just maybe set it up over here for our scratch. And so yeah, my job now is to find the delta. So I like to work backwards from the conclusion here. So I'm gonna start with f of x minus L less than epsilon, and I'm still seeing some people not using these arrows to connect the scratch work steps, and that means that the scratch work is not quite robust enough to be workable. So be sure to use these logical arrows between the steps. So my function, if it wasn't obvious already, the function is 1 over 4 minus x squared. And I'm subtracting negative 1/5, so that's the same as adding 1/5. I want that to be less than epsilon. And what usually happens, guys, which you're seeing right now, is that there becomes sort of an intermediate series of algebra steps that we're going to do. So because we have fractions here that are being added, the best thing in the world to do with that is to make a common denominator. So the common denominator, in this case, we just multiply those two things together, and then we would just have 5 plus 4 minus x squared less than epsilon. Okay, and let me go one more step here. In the numerator, I can take 5 plus 4, and that just gives me 9 minus x squared. 9 minus x squared, let's just factor that.
3 plus x, 3
Uh,
minus x.
You don't look so happy. Are we okay?
Yeah,
Okay.
just multiplying things wrong.
Oh, that happens. So I'm doing my,
Oh, I didn't write down that L was negative. I just wrote that it was 1/5.
oh, that'll get you
Yeah.
messed up every time. Yep, the sign errors are, those are the worst. Okay, anyway, in the numerator here, guys, this is 9 minus x squared, which is a difference of squares. Keep in mind, you ultimately need to get an absolute x minus 3 to show up. Well, I'm seeing it come right now because 9 minus x squared factors as 3 minus x times 3 plus x on top. And then as far as the denominator goes, I might go ahead and pull out the 5 because that's just a constant. And then we have absolute of 4 minus x squared. As you're looking at that, you might be wondering, well, am I going to factor that also? The 4 minus x squared could be factored as 2 minus x times 2 plus x. But, you know, the whole purpose of doing the factoring is to get this, you know, x minus 3 here. Because of the way the limit is x is approaching 3. The denominator is factoring kind of with a base point of 2 and minus 2, which isn't really related to what we've got here. So I would suggest we just leave it the way it is. Okay, now so far, we're still not nearly done yet, because we have not actually done any kind of an estimate here. This is just, everything is if and only if and only if and only if algebra. Right. In fact, if you want, let's just go one more step, because we ultimately do want to get x minus 3 over here being, you know, less than something. So I would recommend you take the 3 minus x and you twirl it around and make it x minus 3, because it's inside the absolute value bars, and move everything else to the other side. So this is going to be epsilon, and then the 4 minus x squared gets thrown to the numerator, while the 3 plus x, oh, and the 5, yep, and the 5. And the 3 plus x gets thrown to the denominator. Okay? And keep in mind, guys, every little piece of this is worth partial credit. So if you get stuck at some point, I would suggest just go on to another problem, leave it where it is, knowing that you've made substantial progress. And if you have time to come back and finish it up, great. But if not, at least you've got a good chunk of it here. This is a good chunk of it. Now, I would love to be able to make this my delta. Right, I would love to do that, except I can't do that because it has the x in it. So what we need now is we need a very important step, which is going to only go backwards. Remember that ultimately at the end of the day, the scratch work needs to work backwards. It needs to work backwards, so I care about this backwards arrow more than anything. So how can I get the inequality to work backwards? Well, I would have to replace this with something smaller than this, right? Because if x minus 3 is less than a smaller thing, then of course it'll automatically be less than a bigger thing. So what I'm gonna write down here needs to be something that is actually smaller than this. Right? Now, if I wanna make a fraction smaller, I have sort of two ways to tweak it. I can either make the numerator smaller, or I can make the denominator bigger. Or I could do both. Right? But the question is like, well, how small could the numerator be and how big, could the denominator be? That depends on what x is. And, x is approaching 3. But, we don't really have any guidance about like, well, what is sort of the biggest value I can plug in for x or the smallest value I can plug in for x? We don't have that guidance unless we do what?
You impose a delta.
Impose a preliminary delta. Okay, I don't know if you remember, we kind of had some examples like this where we imposed a preliminary delta. So I'm going to put a little asterisk here next to this arrow, because down here, what I'm going to do is I'm going to make this assumption. I'm going to assume that delta is already less than, does somebody want to give me a preliminary delta that might be a good choice?
It's not arbitrary, right? It should work with the problem. Like,
It may depend on the problem. It
You
may,
don't want it to equal 2 or -2.
I don't want my x to get anywhere close to 2 or -2. So keep in mind, guys, x is approaching 3. 2 is right here. I really don't want my delta to be so big that some of the x's we're looking at are close to 2. Right? So what might be a good preliminary delta based on that? I might pick 1/2. Even if you pick 1, I mean, it is true, if you pick 1, you will escape from hitting 2. In other words, x won't be equal to 2, but it could be arbitrarily close to 2. And if x is arbitrarily close to 2, guys, then this numerator is almost 0. That's gonna be bad news. If that numerator is almost 0, then I don't care what you put here, you're probably not gonna get it to be less than this, because this thing is 0. So let's pick a preliminary delta that is maybe a little more favorable for us. Let's pick a preliminary delta of 1/2. So I like that idea. So use a 1/2, so let's come over here, assume that delta is less than 1/2. Obviously, you know that when I ultimately write down my final delta, I'm gonna take a min of 1/2 with whatever we eventually calculate to be, okay? So if delta is 1/2, then the x values are gonna range, let me write it as a improper fraction here, 5/2 and 7/2. Okay, so I'll have 5/2. This is my range of x's. In fact, I could write that over here. Then 5/2 is less than x is less than 7/2. Okay, now I'm gonna go back to my comment from before. I would like to replace this fraction with something here that is smaller than this fraction. So I need to take this one and make the numerator smaller or the denominator bigger, or both. Okay, so the 5 and the epsilon are gonna stay the same. How could I make the denominator bigger? Like, what would be sort of a bigger denominator to use than 3 plus x?
3 plus 7/2.
3 plus 7/2, exactly, because x is less than 7/2. So 3 plus x will be less than 3 plus 7/2, which I believe is 13/2. Put 13 halves on the bottom there, replacing our estimate with that. And then in the numerator, I'm gonna make the numerator small as I can, right? So. What value of x in this interval is going to make 4 minus x squared as small as possible? 5 halves, right? Because 5 halves is closer to, well, when I square it, I should say. When I so 5 halves is closer to 2. 2 is the value that would make the numerator 0. So the numerator is gonna be really small if x is close to 2. And the closest to 2 that it can be in this interval would be 5 halves. So I'm gonna use absolute value of 4 minus, and 5 halves has to be squared. So that's 25 fourths. And I do have absolute value bars around that, because in this case, that's gonna come out negative. You guys with me? And let me just clean that up. So 25 fourths, and this is 16 fourths. When you subtract those and take absolute values, isn't that gonna be 9/4?
Yep.
9/4, and then the denominator is 13/2, so now I really am gonna have to simplify that.
I think it's 9/26.
9/26.
No. More than that.
I think it's
5 times
45/26.
9. Yeah,
So so the. Okay, sorry.
Oh, shit, I forgot the 5.
yeah.
Oops.
I have a great excuse today if I have any trouble with this. I didn't go home last night till like 2 a.m. Cause I was grading these unexpected assignment I had to make for my other class. And so I am running on no sleep basically. So that's usually the effect of that gets felt when I start doing this kind of calculation. I think that's 45/26.
Yeah.
Times epsilon. Okay, great. So that is, I just ran out of room here, 45/26 times epsilon. And that is a delta that you can use. Okay, and I'm pretty sure that's the one I came up with in my notes. It sure is. So we're going to now come back over here. We're going to let delta, equal the minimum of 1/2, comma, 45/26 epsilon. That's gonna be my delta. All right, and now I'm gonna just check that it works, so I have to assume that 0 is less than absolute x minus 3 is less than delta. Okay, so then we can say, first of all, we can say that 5 halves is less than x is less than 7 halves. That gets the preliminary range of x values for us. And using absolute x minus 3 less than 45/26 epsilon, we can retrace the scratch. We can retrace the scratch to finish the proof. That's kind of also a rubber stamp that we've used a lot. So once you've kind of figured out your delta, you just have to kind of just lay out a sentence that you're now supposed to retrace the scratch. It's always being retraced backwards. You do need to have these arrows connecting the steps so that imagine you're making a roadmap for somebody who's maybe still trying to learn this stuff. They would need to know how you actually, they would have to be able to figure out from this what you actually meant. Well, you come over here to exactly this, absolute x minus 3 less than 45/26 epsilon, and follow the arrows backwards. That much is good. Okay? Questions on something like that?
So I guess I just have like a quick question
Sure.
about like kind of the understanding of this problem. So like we could have chosen like any fraction for our prelim delta, like
Anything
one-
less than 1.
like 1/3, 1/4.
You could, if you had picked 1/3,
Mhm.
then your other values, the 45 and the 26 would probably also change.
And that's
Yeah.
kind of like my question, like
Uh-huh.
we can choose like basically whatever delta, but it'll still work for.
Right.
I guess I kind of just don't understand like why it works for all of them if
Well-
I choose a specific one.
as long as you picked a delta that is strictly less than one, then your X interval will stay away from two.
Okay,
And I need to stay away from two because I don't wanna divide by zero. So as long as I'm staying away from two, I'll have a range of X values. That I can then play with this expression and say, well, how do I make this thing smaller? Right, I can make it smaller by making the numerator smaller or the denominator bigger. And in this case, I use both of them, okay? But see, that's always going to work, it's just that the range will maybe change a little bit. So like if I had used a delta of 1/4. Then this would have been. 11/4 to 13/4, I think, something like that. And you again will
Numbers
be
just get
able to
messier.
take the two endpoints and plug one of them on top and one of them on the bottom and do a similar estimate.
sure.
Yeah, that's definitely gonna work. The main thing is to make sure that two is nowhere near that interval of X values that you're allowing. Yeah. Does seem okay? I mean, it's a pretty good chance, I mean, we've had a lot of theorems towards the end of the semester that have allowed us to not have to always do these kind of hard. Like, what the easy way to prove this problem now is to say, oh, this is a continuous function. So continuous function, the limit of f of x as x approaches c is equal to f of c. And you would just plug in 3 for x and say, ta-da, that's the answer. And you wouldn't have to really prove it at that point because you're using the power of continuity. F is continuous, this thing is continuous at 3. So I can evaluate the limit by just plugging in 3. So we
Definition, we have to go.
use the definition, right? I'll try at part A, write down the definition of the limit of the function, right? And then part B, use that definition, right? So I know that in recent weeks, we've had some nice results that have allowed us to get our hands out of these mucky details. We haven't had quite as many of these messy scratch work problems because we've had these nicer theorems, but I still think this is a core skill in Math 350, and you should not be surprised if I do ask you to do one of these again. We've seen them enough, we've done them before. I might just if it's something you're still not really solid on, hit me up for some more questions on this before tomorrow for sure. So, okay. Are we good on that? Pretty good on that one? Okay. Let's do, I think this is actually kind of a nice one. Let's come to number 14. Okay, so here's another one. Now we haven't done anything today really about Riemann integration, so I'm gonna bring that back up again. Just to kind of cycle through a bunch of topics. So let's let f be a function from the closed interval a, b to r. Be continuous. Oh, we see that assumption a lot. Right, that means all of our consequences of continuity can be applied and so on. And then I'm also going to let G is another function, but G is Riemann integrable on that same interval. So f is continuous. By the way, the fact that f is continuous means that it is also Riemann integrable. Okay, but stronger than that, it's actually continuous. With one more condition here about G of x is greater than or equal to 0 for all x in the closed interval from a to b. Okay. Now, here's what we're gonna do. We're gonna try to show that there exists a C in the closed interval AB such that the integral from A to B of f times G. So I'll just remind you again, we don't have a nice formula for how to integrate a product. What we did play with this a little bit in that last homework assignment. We had that Cauchy-Schwarz inequality that allowed us to at least put some kind of a bound on it here. But we didn't really have anything definitive we could say. Well, this time I'm actually gonna get some equality that we can say here. The drawback of this formula is, of course, we're not gonna know what C is. But the integral of FG from A to B is going to be f of c times the integral from A to B of just G. Okay. Anything over here where I have written down an integral sign and something in front of that function, you have to know that it's Riemann integrable for that to make sense. So they told us that G is Riemann integrable, so this is a perfectly sensible expression. Now, they did not explicitly tell us that F times G is Riemann integrable, but we know that it is. Because F is continuous, which means it's Riemann integrable. And G is given as Riemann integrable, and in our very last week, this past week, we did finally write down a corollary or a result that the product of two Riemann integrable functions is still Riemann integrable. So we can make sense of this side as well. Okay, so we have that, but somehow it's kind of interesting that the G of X has to be greater than or equal to 0 here. By the way, I should note, maybe I'll do this as the first part of the solution. If G of X is actually equal to 0 for all X. So this is kind of a special case. If the G is actually equal to 0, then you're literally integrating 0. So this would be 0, this would be 0, and it wouldn't even matter what C is. Right, f of c times 0 will be equal to 0 regardless. So in this case, if g of x is equal to 0 for all x, then the integral from a to b of fg is equal to 0, which is equal to the integral of g. And you don't even need to worry about finding a c in that case. Okay. So we can assume that at least somewhere G is actually positive. Okay, so we can kind of assume that. Okay, so we may assume, I guess I'll add that to the notes here. We may assume that there exists an X somewhere, I'll call it X naught, in the closed interval AB with G of X naught strictly positive. Okay, because if there was anywhere that if G was always 0, there's really nothing to prove. Well, guys, F is continuous on a closed interval. We know a lot of things about that scenario. In particular, we know that F is bounded. There'll be an absolute maximum and an absolute minimum for F within this closed interval, right? So let's add that to the solution here. So since F is continuous on the closed interval AB, it is bounded. And again, you guys don't need to know the results, the numbers of the results for the exam, but I will put it here just so you can look it up if you want to. That's proposition 4.8. It's one of the consequences of continuity. And so this just means that there exists a little m and a big M in the real numbers with little m is sort of like the minimum value, so it might be f of, I'm going to say it's f of c1, which is going to be less than or equal to every f of x value, and that in turn is going to be less than or equal to f of c2, which is going to be big M. This is for some c1 and c2 in the interval from a to b. So what we're just saying here, guys, is that f of x is bounded by a lower bound and an upper bound that are both in R. Okay, so they're not going off to infinity. They are definitely bounded between little m and big M. And little m is going to equal f of something. And big M must equal f of something in this situation. So you actually achieve these absolute maximum and minimum values on that closed interval. I'm just assuming that that's happening at these 2 points right here. C1 and C2. Okay, so what I want to do with that now is I want to multiply this chain of inequalities through. See, I have the f of x here. I don't have g of x anywhere in here. And I ultimately need to look at the integral of f times g. So if I've got f set up nicely in that chain, I'm gonna try to multiply through by g to create g throughout that chain as well. And by the way, I am multiplying through by something that is positive. It's not, if you multiply through by a negative number, then inequalities switch directions. So we're assuming here that g is greater than or equal to 0, so it is perfectly safe to preserve this chain of inequalities if we do that. So I'm gonna go ahead and do that right here. M times g of x is going to be less than or equal to f of x times g of x, which is going to be less than or equal to capital M times g of x. This is still for all x in the closed interval from A to B. Instantly, let me just be really clear about something with this. To go from here to here, I'm only using the fact that g of x is greater than or equal to 0. I'm not using the fact that it's strictly positive yet. Because if g of x was equal to 0, then of course everything is totally fine, right? 0 less than or equal to 0, less than or equal to 0. So I don't really care if g of x is equal to 0 in that little calculation. What do you suppose I'm going to want to do with that? Other than this little preliminary base case, I guess it's not really a base case, it's sort of special case that we had over here. There's something in everything that's written down over here that's missing. That I don't see anywhere on the right hand side, and yet it's clearly part of what I need to prove. I don't see an integral sign anywhere on the right side of the board. And we do have a theorem, don't we? That says that if one thing is less than another is less than another, then the integral of the first one is less than the integral of the second one is less than the integral of the third one. Let's hit everything with integral signs. Let's do it. Okay, so then the integral from A to B of m times g is less than or equal to the integral from A to B of f times g is less than or equal to the integral from A to B of capital M times g. Okay. And I can pull that little m out. Okay, because it's constant, and one of our properties of Riemann integrals is that the integral of a constant times a function is the same as the constant times the integral of the function. So I've got little m times the integral from A to B of g less than or equal to, now the middle term, we can't do anything with it, we'll just recopy it, the integral of f times g, and then that's less than or equal to capital M times the integral from A to B of little g. Okay, we getting there?
Yeah.
The thing we are interested in is in the middle. Right? That's for sure. Well. And actually, the thing on the other side of the equation is here. The integral of just g. So, could we do anything?
F of C.
You already said that m is equal to f of c. So we just.
Yeah, the m is equal to f of c2. The little m is equal to f of c1. Honestly, I didn't keep using, I probably, all that was true, was not really helping me. I should have written it down. It's not really the main point here. It's just, yeah, little m is less than or equal to f is less than or equal to big M, and so down here. I've got this chain going like that.
Could you,
Any ideas?
I was gonna suggest the mean value theorem, but
I think so too. Can we write down, let's just write down the mean value theorem. I'm gonna erase this base case here. So how does the mean value theorem for integrals go again? It's something about there exists a C such that, what is it? It's f of c times b minus a is equal to the integral of f, right? So given a Riemann integrable function f on a closed interval from a to b, there exists a c in that interval such that that's true. I'm not so sure that that's going to be the real secret here. It was a good thought. It was a good thought. So I kept harping on how this chain of inequalities follows from this one, even just by multiplying through by g of x, because g of x is greater than or equal to 0. And I didn't make any, what I said was it was not critical at that moment that g of x be strictly greater than 0 somewhere. But if g of x is strictly, so if g of x is greater than or equal to 0, and it is strictly greater than 0 somewhere, then what can we say? Actually, I don't know if that's true. I did not make up this problem myself. I think. Let me just read my solution for a second. Because if my function g. I think this problem is flawed, actually. If my function g looked like this. And this was my x naught, right? So this is greater than or equal to 0, and there exists an x where it's strictly greater than 0, and this is definitely Riemann integrable, but what is the value of that integral?
0.
It's still 0, right? If I just move that one point, remember, if you move a finite number of points, you don't change the value of the integral. So even though g of x naught is greater than 0, the integral of g could be 0. So you know what we need to do? I'm gonna fix this by coming back up here, and I'm going to say let f and g be continuous. Of course, by allowing g to be continuous, then it is still Riemann integrable, but I'm making a stronger assumption now. I don't want my g to do this. If I do have an x where the g of x naught is positive, I want to make sure that I have to actually grab some area from underneath that integral. We did this as a exercise in class, this a group work, I think. So the point being, guys, that each of these integrals of g's are positive. They are strictly positive. So what I'm going to do, guys, is I am going to divide through by the integral of g. So little m will be less than or equal to the integral from a to b of f times g over the integral from a to b of g, little less than or equal to capital M. So just divide through by the integral of g, if that makes sense. Okay. Well. Now we should be in good shape, so the point is, I can use the intermediate value here. This is a number. That is between these two values. And maybe I do want my FFC1 and my FFC2 here, so within the interval from C1 to C2. There will exist a C such that FFC is equal to this value. So let's write that down over here. So I'm going to apply the intermediate value theorem on the interval from C1 to C2, or it could be from C2 to C1. We don't know which number is bigger and which number is smaller. To find a C in that interval, C1 to C2, or from C2 to C1, with f of C equal to that number. The integral from a to b of f times g divided by the integral from a to b of f of g. Thank you. That's it. That's the proof. Now you just move the integral of g to the other side and you're done. Yeah. So this, it looks to me kind of like a mean value theorem for integrals problem, but actually it's just the intermediate value theorem again. That's coming into play here. So you really do have to find the absolute minimum and maximum values of the function. That will occur on some subinterval within the full interval from a to b, and you apply the intermediate value theorem to that subinterval to prove that this number, which is between the min and the max, is equal to f of something. Right? So we're actually applying the intermediate value theorem to f, to just the function f alone. Yeah. I will think about this, again, I didn't come up with this problem, I don't see how to make it work if g is not also continuous. So we'll just make that assumption. That must be on the list somewhere. We'll define it to be true. It sounds good, so it must be true.
There's more on that.
Yeah, yeah, life would be good if it worked. Whatever. Okay, so that's a good one. Okay, let's do another problem. Everybody's hanging in there okay? Yep. All right. So that was 14. By the way, this is probably too difficult. If honestly, the types of questions that I'm putting on my exams, if I myself am like scratching my head and fumbling around with it, I'm probably not gonna go there. It has to be something where I'm pretty much almost sleepwalking through it myself, having taught this 8 times. It should be that easy for me to be able to think I'm gonna put it on the exam. So, but I don't mind doing it because there's a lot to be learned out of it. But yeah, if you're sitting there thinking, oh my God, if you put this on the test, would have any, I would probably be feeling the same way. So try not to let that bother you. Yeah, I'm gonna be really careful. In my review sessions, I don't have to be so careful. I can just say, oh, that looks like a good problem, let's just try it. But then when I write my test, I have to be really careful. Okay, so let's do number 15. Yeah, so now this one, hope I'm not gonna eat my words, but this one I think would be a good test question. This would be more of the right level. Prove that if f and g are bounded and uniformly continuous, I'm gonna use the word uniformly continuous here, on R. So they're uniformly continuous on the entire real numbers, then f times g, so again, I'm gonna take the product of the two functions, is uniformly continuous on R. So the product of two uniformly continuous functions is still uniformly continuous. This one I think, falls more under the scope of sort of more of a standard type of approach. Okay. So, does everybody remember the definition for uniform continuity? It's defined on an entire domain, so remember, it's not just for a point. It's gotta have an entire domain, so, basically, well, let's just start it, let's just start the proof, this is what I'm trying to prove.
Oh.
I'm gonna have a real hard time proving it with that marker.
Almost five.
Let's try.
It's not perfect.
Let me just, I've got a couple more in here. Okay. Let's try this one. Got a couple more that are working a little better. Okay, so the definition is an epsilon delta definition, right? So I'm gonna start off with, this is what I'm trying to prove. So I'm gonna do let epsilon greater than 0 be given. Now, uniform continuity talks about existence of a delta. And we want to prove that delta, but we want to find that delta. But F and G are already uniformly continuous, so I can already find deltas for those, right? So since F is uniformly continuous on R, there exists, what do you want me to call it? I might call it delta 1. I'm not sure it's gonna be the final delta yet, so let's just call it delta 1 for now, greater than 0. Such that, because I'm only focusing on F right here. Such that if absolute x minus y is less than delta 1. I should point out that the x and y have to be in the domain. Of course, in this case, that's not very illuminating because the domain is the entire real numbers. So if absolute x minus y is less than delta 1, then absolute of f of x minus f of y is less than anything we want to put here. Because we're assuming f already has this property. So I don't have to live with epsilon. If we don't know anything better, I would suggest doing one of two things. Either put epsilon here with the understanding that you may have to go back and tweak it later. Or if you're really not sure yet and you think, I bet it's gonna be some trick, put a little box there. Just put it, make it so you're gonna find it again, that you, okay, I've still gotta go back and fill that in. Is everybody with me? If we're assuming uniform continuity, then we can find this delta 1 that makes absolute f of x minus f of y less than anything we want to put right there. We could put a 1 here, we could put a epsilon here, we could put anything, doesn't matter, as long as it's positive. Put anything positive there that we want. Okay, similarly for G. Similarly for G, there exists, I'm gonna call this one delta 2 greater than 0, such that if absolute x minus y is less than delta 2. And again, I won't write it out this time, but x and y have to be real numbers. Then absolute of g of x minus g of y is less than whatever number we want to put in that box right there. Oh, thank you. Okay. Okay. What do you imagine will be the final delta? The minimum of the two deltas, right? Take the minimum of delta 1 and delta 2, most likely, yeah. And John, you said I wanted to use epsilon over 2. Pardon me? Yeah, in these boxes. Well, let's check it out. Let's check it out. So I'm gonna now try to, so let's just do it. Let's just let delta equal the min of the delta 1 and the delta 2. And I'm gonna kick this off by assuming that absolute x minus y is less than delta. This, of course, means that it's less than both of my individual deltas. So I actually know that absolute f of x minus f of y is less than this box, and absolute g of x minus g of y is less than this box. But I need to look at the absolute value. We're proving f times g, right? So that would be f of x, g of x minus f of y, g of y. I need that to be less than epsilon. So now we get to the fun part. How do I work with this? Have we seen an example of sort of how we have to finagle on this one a little bit?
Add and subtract.
Add and subtract something in the middle. They're very good. So we've seen this. We had a theorem for this for continuity. Then we had it for differentiability, right? Then now we're having it for uniform continuity. It's a very common thing to see. So what would you maybe want to add and subtract in the middle? F of y, g of x. Let's try it. So we have f of x, g of x minus f of y, g of x plus f of y, g of x. I'm subtracting and adding the same thing. And then finally minus f of y, g of y. Okay, that's it. So we have to make it a little bit longer before we can make it shorter. And what do you want me to do now that I've added those terms in?
Yeah.
I am gonna factor eventually, but maybe the very first thing.
Rearrange.
Yeah, I probably,
Split
split
it
it up using the triangle inequality. If you factored it now, it wouldn't be the end of the world. You can kind of do that at any stage. Let's go ahead and break it up though first. So I'm gonna take absolute f of x, g of x minus minus f of y, g of x. And then plus absolute of f of y, g of x minus f of y, g of y. Something like that, right? So that's by your good old triangle inequality. We've used this thing a lot, haven't we?
Yes.
Hard to imagine it wouldn't ever come up, right? It seems very likely. Okay, and so now somebody said something about factoring.
Yeah.
So I could do that now, right? So like on this first part, I have g of x in both terms. So I'm gonna do that. So if I factor it out, I'll have absolute of f of x minus f of y times absolute g of x. And then on the second term, I'll have absolute of f of y times the absolute of g of x minus g of y. Okay, and again, we're ultimately trying to get epsilon out of this. So, the way I'm kind of thinking about this is that the whole thing needs to be less than epsilon. I kind of want this part to be less than half of epsilon. I kind of want this part to be less than half of epsilon. That's ultimately kind of what you want. So can we get that to happen? Remember, I get to put whatever I want in these boxes.
Could you just move that small over here?
Can this have x's in it? No, it can't. It has to be a constant. Actually, it has to be a constant. So my problem is the absolute value of g of x is not a constant there, and the absolute value of f of y is not a constant there.
Well, since they're bounded, you can set up another inequality.
Yeah, they're bounded. I was hoping somebody would catch that, right? We have that assumption that the functions are both bounded. So this actually means, and we might even want to go back into our, maybe I'll insert it somewhere earlier in the proof because I don't want to just in the middle of that chain mess everything up. But I'm just going to maybe add it right. I'll just put it as a little asterisk here on the side, right? So since f and g are bounded, right? What that means by definition basically is that there is a positive b. That's whatever my bound is going to be. There's a positive b greater than 0 such that the absolute value of f of x is less than or equal to B. And the absolute value of G of X is less than or equal to B. This is for all X in R.
They can have the same bound.
Well, they might not be, so the F might be a B1 and the G might be a B2, but then I could go back and replace them with the larger one. Now, in that case, you would be taking max, not min. But if you had two different bounds for these functions and you were looking for a single bound that worked for both of them, you could just take the bigger one. Right, so that's why I've already passed to a single bound B here. Okay, yeah, you know, the idea is you wanna make this whole thing less than epsilon over 2, so you need this part to be somehow controlled. As well as the f of y part, they both need to be controlled enough that you can get this, you can pull this off, to get the epsilon over 2 there. Okay, so with that in mind, does anybody wanna tell me what to put in the boxes here now? Epsilon over 2b. All right, let's try it. I'm gonna do the same thing for both boxes. And now I'm gonna come back over here and just work it out. Okay, so this is going to be less than epsilon over 2b times b plus b times epsilon over 2b. And if I clean that up, it just comes out to epsilon. Yeah. That's it. That's it. So if two functions are bounded and uniformly continuous on R, then their product is uniformly continuous on R. Make sense? So I have a follow-up here, which is basically, is it still true if the functions are not bounded? So can I erase this first part? Quick little follow-up on this. So follow up here. Is this still true if F or G is not bounded? So in other words, is it generally true that if you take two uniformly continuous functions on R and you multiply them together, that the resulting function will be uniformly continuous on R? I would certainly suspect that the answer is no. We certainly needed to use that assumption to make this proof work. This proof wouldn't have worked. Maybe now the skeptic will say, oh, maybe there was some other way to prove this first part of your problem here where you didn't need to use a B anywhere. That's what the skeptic will say, is maybe you don't really need the functions to be bounded. So that's why this is a legitimate question, like we have to think about it. Could we have made it work? The intuition though would certainly be no, right? The fact that we've got what I would consider to be about as straightforward of a proof as you could hope for over there that uses the bound B makes it unlikely to me that this would still be true. So if I'm gonna say the answer is no, what do I have to do?
An example.
Counterexample, right? Counterexample would be good. So can somebody give me, so I need an f of x and a g of x. I need functions that I know are uniformly continuous on R. So they have to be uniformly continuous from minus infinity to infinity.
Couldn't one of them just be a constant and the other's a simple function like x?
Oh yeah, what if I use x, right? And then what would be the other one?
2.
2. Okay, so is that uniformly continuous on R? How would you justify that? You can't use the closed interval. You can't say, oh, it's continuous and there's a closed interval because there's no closed interval here. So how would you justify that f of x is uniformly continuous on R since we could do the epsilon delta proof, but I'm wondering if anybody has a slick thing they can tell me. It's a result I haven't mentioned today, but it's actually a pretty big deal, and I made a pretty big deal about it at the time. Is there a tool that we have that you can use that sometimes allows you to say that? Cauchy sequences is more for things that are not uniformly continuous, right? If you have a Cauchy sequence whose image fails to be Cauchy, then the function is not uniformly continuous. But do we have any other tool? This is one you're gonna wanna know tomorrow, guys.
It's because the derivative is continuous.
You're on to the right thing. The derivative, not that it's
Bounded.
continuous,
Bounded.
but that it is bounded. Yes, it has a sort of there's a bound on the slope of this graph, right? So I'm just gonna say, since the absolute value of f prime of x is, well, it equals 1. So this is bounded. So that was, just to give you a reference to look for, corollary 5.4. This would be worth another look. If you haven't really played around with that while you've been studying the last few days, this is a handy way of showing that a function is uniformly continuous on an interval. So the way this statement is made in the corollary is that there is an interval I. And the function has to, of course, be differentiable. Okay, so let's not get carried away. We're not gonna use this corollary if the function doesn't have a derivative. But if it's differentiable like this is, then we can talk about it. So if we take the derivative, yeah, it's bounded, and so therefore it's uniformly continuous on R. Okay, what about this guy? I guess same reason. Or you could, again, just the epsilon delta proof is super easy for this one. But then what's f times g?
2x.
2x, is that uniformly continuous on R?
Yeah.
It sure is, basically the same reason. The derivative, now it's 2, but that's still bounded. So this is not quite going to work for my counterexample. Anybody have a tweak for me?
2x, make make the 2x. So
This
then we
one?
get x squared.
How about we just do that? How about we just use x twice? That way, f times g turns into x squared. And now I'm gonna just check, can I take the derivative? If I take the derivative of this, I get 2x. Is 2x going to be bounded on R? No. Now keep in mind, though, that just because the derivative is unbounded doesn't mean that the function is not uniformly continuous. We have a counterexample for that, which was the square root of x function. I think I did it in the review session for the third midterm. So we need a better reason than using the corollary 5.4. I need a better justification or a valid justification for why x squared will not be. I mean, it seems so reasonable because the parabola, right, it goes infinitely steep. So you're like, yeah, I don't think that's going to be uniformly continuous on R. Does anybody have a reason that they could give me?
We want to say something else.
I have a reason that I can give you. It's irrefutable.
True.
We actually did
This
this,
list.
that should be on this list somewhere too. Where's the one that says, I know I saw this somewhere? Yeah, proof by lost reference. I know I saw this somewhere. Yeah, we did this one in class. I actually created like 2 points x and y that were within some sort of a preconceived delta from each other, and then I squared them both and calculated their difference, and it was more than whatever the epsilon was that I picked. So you basically done in class, oh, sorry, I should say, to show not uniformly continuous on R. Right, so that's a good way to justify that one. Okay. Yeah, so here's I'll just give you one more example, because it's right off this sheet. You guys, if I start giving you things like trig functions or exponential functions and stuff like that, you're really not gonna want to have to do the epsilon delta definitions, because now you're subtracting tangents, or subtracting logarithms, or subtracting quotients of trig functions, secants or something. None of that has, trigonometry does not play nice. Neither does, actually, neither trigonometry nor exponential functions play nice with addition, subtraction, multiplication, and division. Yeah, there's a few identities you can learn, but for the most part, they're not very clean and they're not very nice. So if I gave you something like this, I guess I'll call this number 16. I'm just about ready to wrap this up though, guys. If I said, prove that f of x equals the ln of x, so suppose I took the logarithm here, is uniformly continuous on the interval from e to e squared. Closed interval e to e squared. I asked you to prove that. Now, some of you might say, well, I could just say that it's continuous. Because it is a closed interval. When you're on a closed interval, being continuous and being uniformly continuous are equivalent. But proving that it's continuous, if I could then back up and say, well, I want you to prove that it's actually just continuous. That would be a messy epsilon delta argument. I'm not saying it would be impossible, but it would be, a little bit rocky with the function that you're given here. So what's the easy way to do this?
Take the derivative.
Take the derivative of it, exactly, just take the derivative of it. So the solution would be just take the derivative of this and you get 1 over x, which is definitely bounded on this interval, so. So on the interval from e to e squared, the absolute value of f prime of x, let's see, what would be the sort of the upper bound for it? I do have my x in the denominator, so I would need to plug in the smallest number for the domain that I'm given. So it'd be 1 over e, I guess, in this case. But the point is it's bounded, so f is uniformly continuous on the interval from e to e squared by corollary 5.4. Now, I'm not crazy about this example because using this corollary on a closed interval is a little bit contrived, because after all, if it's a closed interval and you're going to use so if you're using the corollary, then you're assuming that it's differentiable. If you're assuming it's differentiable, then that would have meant it was already continuous, and it's a closed interval, so then it would have already been uniformly continuous. You wouldn't really have needed to use this corollary at that point. All I have to do is open my mouth and say f is differentiable on that domain, and from there you get straight to uniform continuity, right? In fact, that was useful even on that last midterm, right? If there was a function that I asked you, is it differentiable? Is it continuous? Is it uniformly continuous? You had to circle all the right answers, and as soon as you circle differentiable, then you have to circle continuous. And if it's a closed interval, then you also have to circle uniformly continuous. So it's a little bit tricky that way to make a good example of this. But anyway, but this was good. This was good. So yeah, we have a nice counterexample here. Okay. I didn't do well. Of course, we've been doing supremums and infimums with this Riemann integration stuff, but if you feel, I don't think I'm going to do another example of it now, but you might want to go back and refresh your memory about problems from the first part of the course involving supremums and infimums. I'm thinking of things like this, just as an example. I'm pretty sure we did this or something very close to it in class. I just want to remind you when you're proving, so what I usually would do is I'd call that alpha. And then I'd say, okay, I got to prove two things. So I just want to remind you of that two-step structure. Okay. the two-step structure to proving something like this is to first prove that the claimed value is an upper bound, in the case of a supremum is an upper bound. So this is what you need to show. Show that A plus alpha is an upper bound for little a plus capital S. So you first show that it's an upper bound. And then the second part of it is, and this is the part people sometimes forget about, is that you have to do this thing with the gamma, you might remember. So if gamma is another upper bound for S, show that A plus alpha is less than or equal to gamma. In other words, A plus alpha is the best, least upper bound of the set, and the supremum is the least upper bound of the set. So this would be one that you could practice on. It's also true for infimums. You can also do things where you, instead of adding, instead of A plus S, you could do A times S. In that case, you have to be careful about whether A is positive or negative, because if A is negative, it switches the soup to an if. I think we used that last week in that one homework problem, so you do have to remember that as well, but yeah, I really believe somebody coming out of 350 should understand how to make arguments involving supremums and infimums. I mean, we've been doing it all semester. So if you haven't looked at one of those for a month or two, might not be the worst thing in the world to do that.
For
Yeah,
like sup of A plus S, are you gonna give us like what the set
What it is.
defined as?
I would have to define this, yeah, so this would be the set of little a plus little s, where little s is in the set capital S. I would have to give that to you, yeah, for sure. Yeah, so anyway, I won't go over this one now. There's definitely something in your notes to that effect that you could take a look at. But I think I'm gonna have an office hour now. For a little while until I'm gonna take a short break, and then I'm gonna be back. When am I gonna be back? Oh, I have to do a review for my other class from 7 till 9. If you're planning to see me tonight at 9, be patient that it might be more like 9:15. Because, you know, I'm gonna be up in another classroom doing it by the time I get down here. Okay, it's not that I forgot, trust me, I got my schedule all written out for myself. But I might be running a couple minutes late tonight, 9 o'clock, but I will be here. If anybody wants to do their proofs, I think about half the class has done it already. And I've been looking at it, they've been looking really good, so if some of the rest of you wanna get that knocked out, so you don't have to think about it tomorrow, that would be my recommendation. So yeah. Does anybody else have any questions for me though?
Is the
Yeah.
exam gonna be about the same length as a midterm?
I would say it will be more like the same length as the sample final, which is longer than the midterm. So the midterms. To tell you the truth, I had a little bit of an adjustment this class because those midterms were written for like an hour and 15 minutes. Because last time I taught this class, the lectures were only an hour and 15 minutes long. So I was kind of giving you sample midterms and then making my midterm based on that and be similar. But the finals have always been 2 hours, so it will probably be a little longer. If anybody, but I'm also willing to give you some extra time if you need it. Now, if anybody needs to run out of here tomorrow right at 3, because you got another final to get to, let me know. I wouldn't plan my, date of my dreams, meet up with somebody for 3:10 tomorrow afternoon. It's probably not the best time to do it. Maybe reschedule it for a better time. Does that sound okay? So I'll try to give a little extra time. Yeah.
So on the sample midterm, you put something about the hospice rule,
The L'Hopital rule,
Yeah.
but I put it all in there.
Should we review that even though we didn't? cover
If
it?
I didn't cover it in class, then I'm going into this exam thinking you haven't seen it. Now, that doesn't mean I can't put it there and then ask you a question about it, which is what I did with
Yeah,
that last
that's right,
class,
super,
right?
yeah.
Right, so the exam is going to have things for you to prove, right? But they would be things that I would expect a student could figure out. Even if they, well, where is that one? Something like this would be a good example, something where even if you didn't study that particular thing 5 minutes before the final, you could still work it out, right? Or if F and G are uniformly continuous and they're bounded, then F times G is uniformly continuous, right? So those kinds of proofs, whether you studied it or not, I think you could figure it out on the fly. The 7 proofs that are on the sheet, not so much, right? I wouldn't have felt comfortable just saying, oh, I want you guys to write down the proof of the Cauchy is the same as convergence kind of thing. Those are things that, yeah, if you studied it, you probably would nail it. And if you didn't study it, you'd be like, I don't know what to do. I feel a little overwhelmed by it. So that's why I'm doing those proofs on a separate, like I'm giving you the list and I'm, basically telling you they're going to be there. But there will be other proofs, but they will be proofs of things that I'm hoping that you can work through in the fly. And I may also, I probably will have some kind, I'm not gonna do a take-home part, but I might have some kind of throwaway part. Like, okay, I don't wanna do that problem, but
Can't remember that.
I don't remember that. I'm blanking out on this, so I might even do more than one of those, depending on after I write the questions, how I feel about them. Like
How long the exam is?
and how much time. I don't like to do too much, like I don't wanna make like 50 hard problems and so there's 50 hard problems here, you can throw away 48 of them. That's kind of silly, cause then people don't know how to like,
How do we study?
how do you put your time in the 2 hours to figure that out? So, but I probably will, like, I understand as well as anybody, I was a student not that long ago, that anybody can blank out on anything on any given day. And I like there to be a little bit of sort of built-in forgiveness for that. So in the midterms, that was the take-home thing. But I don't feel like I can do take-homes during finals week. I told you that before. So instead of that, I might, as a substitute for that, just have like a throwaway thing. Or maybe I'll have a thing where you can do everything, and then I'll just cancel out whatever your worst thing is, something like that. So I'm still working on the test though. So I can't be too specific. I am gonna be around tomorrow. I'm hoping to get in by 9-ish. I'll be on the early side tomorrow. So if you have any questions, or if there's just topics, you're like, oh gosh, I just don't feel like I'm very good at doing the definitions of derivative or whatever it is. You can come on in and we got a whiteboard in here. I'll try to come up with something to give you a little practice on the spot. If you just need to kind of have that sort of focus, feel free to do that. Or even if you just need a place to kind of be in math mode, feel free to do that. I'll open up the room down the hall. You can always hang out in my office. All of that's an option. Sound good? Reasonable?
Can we do the proof?
You can do them tomorrow morning. You can do them today, tomorrow, anytime I'm around. I'm gonna be gone from, like I said, I'm gonna have dinner and then do a review from 7 to 9. Other than that, I'm gonna be basically here. I went home last night at about 3. So,
Why were you here at 9 in the morning?
because I had things to do.
Oh my God.
You think only the students are stressed out during finals?
No, I don't.
I had so much grading to do last night for my other class that I was on a roll, so I was like, I'm just gonna stick with it. Is everybody out there in Zoom land catching all this? Are there any questions, guys?
No,
That's great over here.
we're all good.
Good on your end? Okay, so I'm around and I hope that you'll stop by if you've got questions. I'm gonna end this session here, but I'm gonna go right over to my Zoom office for the next approximately an hour. If you got questions, you can go straight over there now. Otherwise, I'll be around later tonight. Thanks for coming.
Sounds good.
Bye, guys.